Hi! Today's video is going to be about, as the title says, graphing systems of linear equations. So by the end of this, hopefully, you'll be able to do the following. First, you need to be able to explain what a system of equations is and what the solution to the system represents. Second, we're going to be looking today, as the title said, to finding solutions graphically. We're going to stick pretty much with just linear equations, although at some points I will tell you that some of the things we're going to do today will work for bigger and uglier systems as well. Third thing you'll need to be able to do, primary focus will be using technology, the graphing calculators for example, in order to find those solutions. And I should give you enough time in class. You should be able to do all of your problems as long as you're working during class time. However, if you have to take them home, you might have to do your graphing by hand. The last thing, linear equations systems of linear equations come in different types, and you need to be able to identify those types just from the equation, not from the graph. Excuse me. If you have to do your graphing by hand for any of this assignment, the two most important words become be neat. If you use graph paper, if you try to do this by hand, by setting up your own coordinates, and suppose when you draw your line, you're not very careful about it, I'd recommend using a straight edge if you have to. Very small bit of sloppiness will make your answer come out completely wrong. So you just need to be sure, if you're reduced to doing these by hand, take your time, make sure you do it right, make sure you do it neatly so that the answer comes out correct. Okay. A system of equations is a group of two or more equations that use the same variable. Some of you might look at this part here that they use the same variable and think back to the assignments you were doing last week. Well, all those used x's and y's. What I mean here about the equations using the same variables is that the x's and y's in a certain problem, which will have multiple equations, represent the same values. When we get down to the word problem that comes later on during this lesson, you'll see that in both cases, x represents some amount of time and y represents some, I think it's height. We'll see that when we get to the thing. But both equations have x and y. Those x and y both represent the same things. Now the solution to a system is the values of the variables that make all of your equations true at the same time. The whole point of a linear equation is that there are a lot of points, x comma y, that work for each line, an infinite number in fact. But here, since we have multiple equations, there might only be one point, x comma y, that work. Or if our system eventually gets bigger to x, y, z, for example, there will be one value for each variable that works. When we get up to those larger systems, one thing you need to remember is however many variables you have, that's how many equations you need. So if you have unknowns w, x, y, and z, you need 4 equations, and that's be quite a challenge to do those, but that's how many you'll need to be able to do the thing. Oops, I meant to take that line out because it kind of gives away the whole deal. Since I forgot, no problem. The solution is where the lines intersect. When we see the first graph, you'll understand why. So let's get to that. So here's the system. Notice I have two equations. Y equals negative 1/2 x minus 7/2, and y equals 2/3 x. To show this is a system, I have this open bracket or open brace, whatever you want to call it, that engulfs both, opens onto both of these equations that show they're together. So I went ahead on this first example and graphed it myself. So the green is that first equation with the negative 1/2 slope, and then the 2/3 slope, I think it was. Yeah, the 2/3 slope is the one in red. All the points on green represent an XY combination that work for that first equation. All the points on the red line represent an XY combination that works for that second equation. The only point that works for both of these is right there on both lines. And let's see. Ooh. Try it again. -3, comma, -2. Goodness. Don't worry, I was switching my tablet here later for all the other stuff I have to do handwritten, not to rely on the mouse. But you would still, since that's a point, write it as a point, x comma y. -3, -2, that is the solution, that's the point that works for both equations. Example. Here's the word problem example. You can read through it yourself. But basically they give us these two equations where x is time measured in months, and y is our height measured in centimeters. Evidently Joe and Ed are not people. Now this is the system they're giving us. So again, I'm going to switch back over to the tablet so I can do this by hand. Alrighty, there it is. Hopefully this is showing up on the video. Switch to red. First equation. I'm just going to skip that first step. Hopefully we can all see and just add the 3x over. Now I'm going to divide by 4. 3 divided by 4 is 3/4. And 12 divided by 4 is 3. Got to remember, we're dividing the entire equation by 4. Alrighty. Now, the blue. 2y equals x plus 8. Just added the x to the other side. I'm going to divide by 2. 1/2 x is 1x divided by 2. And 8 divided by 2 is 4. I'm not going to rewrite it this time. I just want to say those are the two equations. So now I shift back, erase what I had in there from the previous example, and put in my new two equations. 3/4 x plus 3 and 1/2 x plus 4. Now notice in this particular example, all the stuff over here doesn't really exist. It has no meaning for this problem. You can't have a negative number of months. But we can see our intersection up here. So again, I want to analyze the graph. I want to find the intersection of the two lines. Click, click. And 4,6 is the point we're looking at. 4,6. Holy moly. All right, at what, now the original question is at what month, and X appears to be months, so we would write month 4, and that would be our final answer. Okay. Next, we're looking at the types of systems of equations we could have when we have two lines. Well, we can have what we've already seen. Two lines that intersect, they meet at one point right there. That's fine and dandy. Well, that gives us that one solution, that point where they meet. What else could two lines do? Well, they could be parallel. By definition, how often do parallel lines meet? Exactly, they don't, so there are no solutions. Then there's a third thing two equations could do when you graph them. They could graph is the exact same line, which means since both equations are really identical, every point on the line works for both equations, which means we have an infinite number of solutions. So we could have one solution, infinite number of solutions, or no solutions. Now suppose we have some sort of solution. If the two lines are doing different things, they're said to be independent. However, if they rely on each other and they're doing the same thing, they're dependent. So we need one of those two. If we don't have any solutions, we call that inconsistent. So consistent have solutions, and those are either independent or dependent, depending on if the lines are different or the same. And if we don't have any solutions because we have parallel lines, because we're inconsistent. So now what we want to do is look at an example. And we want to tell what kind we have without graphing. We need to get these into their forms so we can tell whether we have parallel or intersecting whatever we have. So, read for the first one. Y equals negative 3x plus 5. Well, that's handy. That's all we needed to do. Second equation. 5y equals 10x plus 2. We need to divide everything by that 5. 2x plus 2/5. Now what we need to do is look at our slopes. That one is changing by negative 3. It's down 3 over 1. This one is climbing by 2 over 1. Those have completely different slopes. They're completely different lines. So these are independent systems. Let's try another one. Okay, well, actually, this first equation is already set up. Y equals. That's handy. Just to say, stay consistent, I will switch over to blue. 2y equals 4x plus 6. Divide the 2, 2x plus 3. Well, now look what we have. Y equals 2x plus 3. Y equals 2x plus 3. These equations, when we simplified them, came out to be the exact same thing. So these are dependent. Have an infinite number of solutions to them. Well, let's do it really quick so we can see what we have going on. Y equals 5x plus 5x minus 3. Switch the color. Come on. Negative 2y equals negative 10x minus 3. Y equals 5x plus 3 halves. Slope's the same, but we're starting from different points. So these are completely different lines, but they are parallel. And because they are parallel, they will never meet. There will never be an answer that is an inconsistent system. Okay. We just did all those. The homework assignment. Page 118, 1 through 9, which those will be graphing ones. And you'll want to try to get those for sure out of the way in class using the graphing calculators we have in the room. Then 13 through 24 are using, just like we did in these last examples, where you get into y equals form and then tell me what kind of system we have. All right? Thank you.